Lake Oroville is at 98% of its total capacity today. The Department of Water Resources says Feather River water releases are at 5,000 cubic feet per second to meet downstream delta water quality and outflow.
In the quiet hours before sunrise, something at California's Lake Oroville broke every expectation. The numbers jumped fast, the shoreline shifted, and the timing made no sense. This wasn't a slow rise or a seasonal change. It happened while most people slept. Engineers checked twice, then checked again. What they saw raised more questions than answers. If this lake can move like this overnight, what does that say about what's happening out of sight? One detail in the data stands out, and it changes how this surge is being viewed. The sudden surge event. In the early morning hours, monitoring systems at Lake Oroville detected an unprecedented rise in the reservoir's water level, 23 feet in just a few hours. At 2:17 a.m., sensors recorded the surface at 847.3 feet. By 6 a.m., it had climbed to 870.1 feet. Such a rapid increase had never been documented at the lake.
Lake Oroville is 894 feet elevation, and its storage is around 3.45 million acre feet.
And no manual readings or operational logs contradicted the data. Multiple independent systems confirmed the surge. Backup gauges matched electronic sensors within inches, and technicians cross-checked the numbers using several monitoring methods. The rise showed no pauses or irregularities. At sunrise, on-site staff verified that the equipment was functioning correctly and confirmed a visible inland shift of the shoreline by more than 60 feet. Physical evidence supported the readings. Structures near the water's edge were partially submerged. Buoys had shifted from their normal positions, and driftwood rested far below its usual high water mark. A supervisor's log captured the moment simply. The shoreline had moved. This was not a sensor error or data glitch. It was a real and sudden increase in water volume, estimated at billions of gallons. Officials were initially puzzled. Lake Oroville, California's largest reservoir and a cornerstone of the state's water system, does not behave this way without clear causes. There had been no heavy rainfall, no known upstream releases, and no visible triggers. Yet any anomaly at Oroville carries statewide consequences, affecting water supply, power generation, and agriculture. The unexplained surge immediately raised concerns. Memory played a crucial role in amplifying anxiety. The Oroville spillway disaster in 2017 caused the evacuation of nearly 200,000 residents, and that incident still has a profound impact on the community, so that any unexpected change is regarded as a serious issue. News about the rise spread uneasily, and the fears re-emerged even before the officials could give explanations. Celebrants repotted quickly, knowing that every foot of water meant tremendous pressure on the dam. This was not the normal seasonal increase. It was a sudden spike without a specified reason. As the water level kept rising, the most significant question came: was this a harmless anomaly or a sign of a deeper and more dangerous issue? Around mid-morning, the California Department of Water Resources set up an incident command structure. Teams were dispatched to inspect the area around the reservoir, while monitors for environmental conditions started to keep track of the effects in the river downstream. Every sensor's data was checked repeatedly. The surge could not be attributed to any conventional flood event or human activity. The consequences would be grave. Lake Oroville is a major source of water for millions of Californians and provides hydroelectricity and support for agriculture. A sudden increase of such size overnight could lead to disrupting those systems. Transitioning from the sheer scale of the event to the process of elimination reveals just how thorough and perplexing the investigation soon became. Eliminating the usual causes. Engineers began their inquiry by methodically crossing off every common explanation for a sudden reservoir surge. First, they examined weather data with a fine-toothed comb. Doppler radar and regional precipitation reports confirmed there had been no rainfall over Lake Oroville or its watershed during the previous 72 hours. The skies were clear, with no storm systems crossing the Sierra Nevada to introduce new water into the basin. Next, attention turned upstream. Reservoir operators and dam managers were queried to uncover any simultaneous gate releases or emergency overflows that might explain a surge downstream. Every single upstream facility reported stable, authorized outflows, no unexpected discharges. No gate openings had been ordered, and no records showed changes in water release schedules. This eliminated the possibility that human-controlled dam operations were behind the rise. Seismic monitoring stations were consulted to determine whether a landslide or sudden earth movement had introduced debris or displaced water. The seismic data revealed no landslide signatures or impactful earthquakes that could have generated such a swift volume change. Satellite imagery supported this by showing no fresh sediment or debris entering the reservoir that night. The Feather River's stage remained steady, ruling out flash floods or hidden surges caused by sudden runoff. Weather stations across the region also reported normal seasonal temperatures and wind speeds. There was no unusual climate activity that could have triggered evaporation shifts, atmospheric pressure changes, or other physical effects pushing water levels rapidly. Every environmental check painted a consistent picture. The lake's surge had no surface or atmospheric cause. This process of elimination forced investigators to rethink traditional hydrological models. Water input was not coming from above, nor from controlled human releases. Neither natural flash events nor visible geological disturbances could account for the data. As each familiar cause was dismissed, the unknown grew more ominous and complex. The technical teams examined the whole sensor and measurement system very closely to rule out any possibility of instrumental errors or data glitches. The consistent rise was perfectly indicated by the independent devices of different types, like backup gauges, telemetry stations, and even visual inspections on the ground. The instruments were not failing. The water was actually moving. After ruling out surface causes, engineers started looking into hidden processes below the reservoir. There was a rise in the lake's waters, but the question was, from where? What could the invisible source be that had the capacity to push billions of gallons of water in such a short period of time that it could hardly be explained? These inquiries became more pressing as the crews on site noticed changes in the shoreline that matched the readings. Flooding of lands that were dry for a long time, buoys being moved out of their positions, and roads underwater becoming inaccessible. At the same time, control rooms and incident centers were coordinating the notifications to the federal agencies and water districts that were downstream cut off. This network of stakeholders was deeply aware of the weight of the abnormalities' implications. The flooding was a signal for immediate vigilance, but it also revealed the lack of knowledge about some of the lake's dynamics. The unprecedented nature of the occurrence turned into a demand from the state to provide its best experts. Ruling out every visible and conventional trigger meant that the investigation was now looking beyond the ordinary, to the deep, unseen parts of the lake and its foundation. Clue number 1 was going to be here, concealed in the chemical fingerprints that were left in the water itself. The water's mysterious new chemistry unveiled secrets pointing far below the surface, changing the entire narrative. Chemical clues in the water. Samples collected from Lake Oroville during the surge revealed chemical signatures far from what would be expected in surface runoff or rainwater.
Increasing releases out of Lake Oroville to preserve storage in the lake for flood protection.
Laboratory analysis showed elevated levels of lithium 4 times higher than typical surface water concentrations. Alongside this, boron was detected at levels matching those found only in deep geothermal systems, suggesting water had interacted with heated subterranean rocks. Further investigation into rare earth element ratios indicated that the water likely spent decades in contact with basement rock far beneath the surface. These minerals form only under intense heat and pressure, conditions impossible to recreate in shallow aquifers or surface flows. Stable isotope analysis of oxygen, 18, and deuterium isotopes painted an even stranger picture, falling outside familiar local precipitation ranges. This told scientists the water's origin was not recent rainfall or snowmelt, but derived from far deeper and older sources. X-ray diffraction techniques identified mineral phases such as zeolite and chlorite, compounds formed through sustained geothermal activity. Geological processes occurring deep underground were influencing the chemical makeup of the water flooding into the reservoir. This evidence suggested the reservoir was being fed by an underground source connected to deep aquifers, rather than surface waters. Such isotopic and chemical anomalies challenged established hydrological assumptions about the reservoir's inputs. If the water was rising from below, it implied the existence of conduits linking deep geothermal reservoirs to Lake Oroville's basin, fractured fault lines or fissures created by geological stress. These pathways could allow confined groundwater under high pressure to surge upward rapidly. This explanation fits with the timing of the rise, which occurred overnight when monitoring might be less intensive. The unique chemistry matched what could emerge from deep sources rather than surface contamination or routine inflows. Still, scientists lacked direct imaging to confirm active conduits. The idea remained a working hypothesis pending further verification. The discovery of these chemical markers shifted concern from typical surface water management toward the complex geology underneath the reservoir. It suggested a dynamic and unknown interaction between the lake and deep aquifers that had not been accounted for in previous safety models. The possibility that deep groundwater was pushing massive volumes into the lake overnight altered the risk landscape dramatically. Understanding these chemical clues also raised new questions. How long had this subterranean flow existed unnoticed? Was it a new occurrence or an intensification of a slow process? Could these deep waters continue to feed the reservoir indefinitely, or would the surge eventually subside? Each question added urgency to ongoing monitoring efforts. The complex chemistry painted a portrait of Lake Oroville as a reservoir influenced not just by surface hydrology, but by hidden forces far beneath it. This realization reframed the investigation and expanded the scope of what state engineers and scientists needed to consider in assessing the dam's stability and future risk. As these chemical insights unfolded, another set of data was emerging. Subtle seismic tremors beneath the lake, hinting at movements within the Earth itself. Seismic activity below the lake. As scientists unraveled the chemical mystery, their attention turned to subtle tremors shaking beneath Lake Oroville's eastern arm. Seismic records revealed a cluster of microquakes, small, ranging from magnitude 1.2 to 2.1, that began just as the water surge started. Though minor in strength, their timing was strikingly precise, suggesting a connection to the rising reservoir levels. These events hinted at unseen movements deep underground, stirring concerns about shifting rock or widening fractures. Fault zones mapped decades earlier crisscrossed the lakebed, known to be fractured and permeable in places. Such fractures could act as conduits between deep aquifers and the reservoir, opening pathways that groundwater under pressure might exploit. Even low-magnitude seismicity can trigger subtle shifts, enough to create or expand these underground channels. This raised the possibility that water was not merely seeping in slowly, but flowing rapidly through newly formed geological pathways. Microseismic episodes like these are often precursors or indicators of changing stress regimes in the Earth's crust. In dam engineering, they are taken seriously because they can signal instability or evolving conditions that affect the reservoir's foundation.
The dam was in danger of failing. Water continues to burst through the eroded spillway, prompting fears of mass.
The coincidence of the quake cluster with the sudden water rise was more than correlation. It suggested cause and effect had entered a dynamic phase. Yet, direct imaging of these fractures or flows remained elusive, leaving much to interpretation and investigation. This geological perspective offered a framework to interpret the water chemistry findings. Water historically confined in deep geothermal reservoirs could have been forced upward by pressure, traveling through these seismic-triggered fractures. The hypothesis fits both data sets, chemical signatures indicating depth and heat, and the shaking events implying mechanical changes in the Earth. Together, they depicted a scenario where natural underground forces suddenly influenced a major surface water body. Despite this, scientists emphasized caution in drawing firm conclusions. Microquakes of such magnitude are common in tectonically active regions, and not all translate into significant hydrological changes. The precise location, extent, and permanence of any active water channels beneath Oroville were still unknown. Questions mounted. Was this a one-time surge linked to a transient fracture event, or the start of an ongoing subterranean inflow? Microseismicity brought up safety issues and concerns for the dam. Even if the earthquakes weren't big enough to damage the structure, their existence close to the vital facility still needed very close scrutiny. The engineers very carefully monitored the dam's embankment and compared the historical seismicity with the new activity in order to assess the risks. The uncertainty of the oil and gas interactions and water flow gave rise to a new layer of complexity in an already delicate situation. Residents and emergency planners were watching the scientific developments with growing unease. The residents were constantly reminded of past crises and coupled the lake's unfamiliar behavior with anxiety about what would happen next. The silent trembling under their houses was like the invisible threat that was rising in the reservoir, one that was earth, water, and human infrastructure mixed together in an uneasy balance. The differences in pressure between the confined groundwater and the reservoir surface level might be the reason for the huge volumes of water moving upward, but it was still unclear if these pathways would continue to widen or get shut off completely. The uncertainty led to a broader tension, the forces of nature interacting with one of mankind's largest water projects in ways that were not predictable. The officials acknowledged the urgent need to map these underground movements better, and that even if the lake surface was going up and down, they still needed to do so. As the seismic clues were deepening the mystery underneath Oroville, the engineers returned their full focus to the dam itself. The rising water levels, coupled with the subsurface activity, warranted an inspection of the internal condition of the dam, where invisible damage could be the greatest danger. The signs beneath the reservoir led directly to concerns about the dam's structural integrity, where unseen processes might be weakening one of California's most critical assets. Potential dam integrity issues. The possibility that something inside the dam was changing gained momentum as technicians monitored internal systems. Evidence of internal erosion, known as piping, began appearing in sensor data from the dam's east gallery. Piping occurs when water finds and enlarges pathways through embankment soil, washing particles away and gradually hollowing channels that threaten stability. This silent process can advance far before surface signs emerge, making early detection crucial. Drain outputs along the dam showed spikes in turbidity, cloudiness caused by suspended sediments, indicating disturbed materials inside the embankment. Simultaneously, embedded piezometers, which measure water pressure within the dam, registered irregular and deteriorating readings. Some of these pressure anomalies mirrored patterns last seen during the 2017 crisis, raising red flags among dam safety teams. The close timing of these sensor changes with the overnight surge suggested the dam itself might be responding to or contributing to the water increase. Historical dam failures from piping underscore the stakes involved. In 1976, the Teton Dam in Idaho collapsed following internal erosion, while the Sardoba Dam in Uzbekistan failed recently under similar circumstances. These disasters serve as grim reminders that unnoticed internal damage can rapidly escalate to catastrophic failure. The patterns emerging at Oroville resembled early warning signs in those past collapses, making prompt assessment critical. One of the dam's safety team's immediate challenges was distinguishing whether pressure changes were caused by new water pressures entering from below, or by worsening internal seepage. This distinction carries enormous implications for repair strategies and public safety decisions. If the water was invading from the deep aquifer, the problem might be more geological and localized. But if it was moving internally through the dam, that suggested a failing barrier and urgent risk. To ensure objectivity and reduce institutional bias, an external engineering expert was called in to audit the investigation. Her charge was to verify data, question assumptions, and maintain transparency, vital given the fragile trust that remains since the 2017 emergency. This step underscored the seriousness of the situation and the commitment to avoid past mistakes in data interpretation and public communication. Advanced testing commenced, including dual isotope analyses conducted by a second laboratory to confirm water origin findings, acoustic Doppler current profiling to detect underground flows entering the reservoir, and detailed piezometer gradient studies to map pressure changes. The results would take time, but promised to clarify whether internal erosion was active and whether new seepage pathways endangered the dam's core.
Balancing conservation with flood prevention and planning for whatever comes next.
Meanwhile, field crews faced challenges inspecting the dam embankment directly. Ground instability and saturated sediments limited access in some areas, complicating visual assessments. Safety protocols required detailed photographic documentation of every anomaly found, ensuring a thorough record as the pressure on the dam increased and the water rose further. Every small detail became a potential clue in understanding the evolving condition of the dam. The situation demanded swift action, but balanced against the need for methodical analysis. Engineering teams worked to prevent alarmism while preparing for all scenarios. The potential for catastrophic failure cannot be ignored in dams of this scale, especially with rising water testing structural limits and hidden vulnerabilities. The next days and weeks would be decisive in determining whether the dam's integrity was holding or eroding beneath the crisis. As experts focused on these internal threats, the community downstream prepared for any eventuality. The survival of millions depends on swift, informed decisions, yet uncertainty still reigns. As the lakes rise and what lies beneath remain enigmatic forces shaping California's future. The story unfolding at Lake Oroville is as much about engineering and geology as it is about human resilience and vigilance amid uncertainty. Human impact and community response. As Lake Oroville's water level relentlessly advanced, the residents along its shores felt the pressure mounting not just on infrastructure, but on their daily lives and sense of security. For many, the surge dredged up vivid memories of the 2017 crisis, the year when emergency spillway damage forced the largest dam-related evacuation in American history. That trauma still lingered, shadowing every new anomaly with fear and distrust. Families who once fled in the dead of night found themselves bracing again, this time with a quiet but persistent dread. Maria Delgado, who lived on Lakeshore Drive, watched anxiously as the water crept closer to her property. Her neighbor's dock, installed just 2 summers prior during drought conditions, now lay submerged. The access road to the marina, which was designed to accommodate dry seasons, was muddied and impassable well before spring's usual rise. Despite calling the county emergency line twice, Maria was met with the same cautious response. Situation under investigation. No evacuation order yet. Her resolve hardened. This time, she wasn't waiting for an official warning. This anxiety was shared across the community, where preparedness had become a way of life. Emergency kits sat packed, gas tanks remained full, and escape plans were kept updated, not out of paranoia, but hard-earned practicality. The invisible threat of rising water forced residents to live in a state of constant alert.
The state's future depends on learning to manage both sides of the water coin,
where even routine events carried the weight of uncertainty. Psychological stress mingled with physical reality, creating an environment where every siren or shifting shoreline lingered in deep-seated unease. Local authorities understood the challenge of balancing urgent communication with preventing panic. The California Department of Water Resources Incident Command Structure was activated quickly, aiming to coordinate inspections, monitoring, and notifications. But the silence from official channels on evacuation orders left many feeling stranded between hope and fear. This gap intensified suspicion among communities still coping with past trauma, further complicating emergency management efforts. The upswing's ripple effects moved further and affected rural agriculture as well as urban centers. The water allocations that were so vital for Central Valley farming hinged largely on Oroville's reliable levels. Any disturbance could cause not only a direct loss of crops, but also the loss of entire economies and the food supply chains contracted by them. Urban service providers, who depended on uninterrupted water supply and hydroelectric power, were looking for reassurance that the crisis had not yet put them in that situation when they were already quite nervous. The problems of humans went further than the physical dangers that were not immediate. The ties that had made the communities last for a long time were put under strain by uncertainty and a feeling of helplessness. A family like that of Maria's had to bear the question all the time: if the dam broke, would the help come in time? For a large number of people, the surge opened up years of trust and changed it to doubt about the institution's readiness and their communication. This worry of the society was heard and felt.
This massive body of water holds the fate of 27 million people in its depths.
In the homes and public gatherings, just like it was a whisper. Emergency personnel and inspectors working day and night shared the community's fear. Ground instability made the teams give up some ways because the soils being too wet. These conditions not only highlighted the environmental difficulties, but also the human cost of working in such a dangerous area. Every waterline change was a signal that history might be repeating itself, and every move made was a battle against time and nature. Communities, though, showed their strength even in the midst of fear. Some neighborhoods joined together, exchanged resources and information. Preparedness went from being an individual effort to being a collective one, thus revealing a very human response to crisis, hope in the middle of uncertainty. This unity provided a weak but important balance to the rising water and complicated technical problems. However, even when the residents were getting ready for the unknown, the larger effects of the water surge were being felt at the opposite end of the river, where the ecosystems and the regulations were also fighting their battles. The mounting human tension set the stage for a deeper look at how the surge was impacting the environment and the institutions charged with managing California's water future. Ecological and regulatory concerns. The sudden influx of water at Lake Oroville.
Lake Oroville reached its all-time low level, 643 feet above sea level.
Did not just threaten dams and homes, it sent shockwaves through the downstream ecosystems that depend on finely balanced river flows. Environmental monitors quickly registered alarming changes. Turbidity levels rose beyond thresholds suitable for salmon spawning, while sediment mobilization risked releasing heavy metals previously locked in reservoir deposits. These shifts posed immediate threats to aquatic life that had adapted to decades of carefully managed water regimes. Fish populations, particularly those of salmon, face critical challenges when sediment and water quality thresholds are exceeded. Raised turbidity disrupts spawning beds and degrades habitat quality, potentially jeopardizing reproductive success for vulnerable species. The timing of the surge, sudden and unanticipated, left ecosystems no time to adjust or recover, creating ripple effects that could cascade through the food web. Scientists and environmental groups watched closely as early warning signs emerged downstream. Water treatment plants serving nearby communities also reported changes in source water chemistry, complicating the already delicate task of providing safe drinking water. Altered chemical profiles meant that treatment protocols had to be reassessed quickly to ensure contaminants remained within safe limits. The surge's cascading impact underscored how interconnected reservoir management and urban water security truly are. The event also spotlighted long-standing tensions within California's water governance. Agricultural districts demanded clear answers and assurances to protect their irrigation allocations, critical for food production and regional economies. Urban agencies, facing growing populations and climate pressures, pressed for stability in supply and infrastructure resilience. Environmental advocates, meanwhile, questioned whether past operational decisions and aging infrastructure had weakened the system's capacity to absorb and respond to such anomalies. These competing demands created a complex political and institutional landscape where scientific uncertainty became entwined with competing priorities. Some stakeholders quietly favored the natural aquifer explanation of the surge, which would limit liability and avoid blame on infrastructure management. Others suspected internal dam seepage pointed to deferred maintenance or monitoring failures, potentially exposing institutional negligence. The conflict moved beyond science, touching deeply on trust, accountability, and governance. Adding to the complexity were shifting climate patterns. California's hydrology no longer matches historical norms. Intensifying droughts, punctuated by heavy precipitation events, have compounded stress on reservoirs and dams originally designed using 20th-century models. This evolving backdrop means anomalies, like Oroville's sudden surge, could become more frequent, challenging operators and regulators to adapt more rapidly than ever before. Regulatory bodies faced the dual challenge of responding to immediate risks while planning for long-term resilience. The surge tested the effectiveness of inspection protocols, data transparency, and emergency preparedness. Questions about the adequacy of current monitoring networks and maintenance schedules took center stage. The situation demanded not only technical fixes, but institutional reforms to bolster trust and responsiveness. Meanwhile, environmental impacts underscored the urgency of balancing human water needs with ecosystem health. Protecting fish habitats, water quality, and downstream communities required integrated strategies capable of navigating uncertainty and emerging threats. This event became a litmus test for adaptive management in a changing climate. This uncertainty leads directly to the ongoing mystery of the surge's origin and the grave risks that remain hidden beneath the lake's rising surface. The unfolding mystery and future risks. Despite extensive data and ongoing analysis, the core mystery behind Lake Oroville's overnight surge remains unresolved. Scientists still cannot pinpoint where the sudden influx of water came from or whether it will continue. One leading concern is a deep, unmapped underground source feeding the reservoir through fractures beneath the surface. If true, its size and duration are unknown, making risk assessment and emergency planning far more difficult. Uncertainty also surrounds the dam itself. If internal erosion is quietly progressing, the consequences could be severe. Monitoring systems have not yet confirmed structural failure, but the possibility that the dam is weakening without clear surface signs keeps engineers on edge. At the same time, the surge's abrupt timing and accompanying microseismic activity suggest unstable conditions below the reservoir that could either settle or intensify without warning. The decision-makers are now under enormous pressure. The evacuations could save lives, but at the same time, they would be a big disruption to community and economic activities. And on the other hand, the delay in decision-making might cause loss of opportunity to notice the warning signs. The psychological impact of the 2017 evacuation is still very strong. So every choice is made with utmost care and anxiety. Climate change and aging infrastructure further complicate such decisions.
And who could forget the Oroville Dam spillway crisis that threatened hundreds of thousands of homes?
The Oroville Dam, which was built more than 50 years ago, was designed to withstand conditions that are not fully applicable anymore, as the new weather extremes are putting the old systems under new stress. The issue of trust is also a very tentative one. In acknowledgement of the fact that past mistakes have been very damaging, an independent engineering assessment was commissioned to promote openness and bolster public trust. In the meantime, scientists are still investigating the mystery using state-of-the-art equipment to create maps of unseen water routes and to find out if the water source is finite or continuous. For the people who rely on Lake Oroville for water, electricity, and agriculture, the risks are tremendous. The flooding event serves as a reminder that current-day infrastructure is still very much susceptible to what may be forces of nature not entirely understood yet. Lake Oroville's mysterious surge is a stark reminder that critical infrastructure is shaped by forces we don't always see coming. As experts dig for answers and weigh the risks, millions are left watching, waiting, and wondering what happens next. If this deep dive gave you new insight, support the channel by liking the video and subscribing for continued updates as the situation develops. And when this ends, don't stop here. Let the next video that appears on your screen take you deeper into what could unfold next.